Hi all, in this session we are going to study about the hydraulic dynamometer, one of the torque measuring instrument. In the diagram you can see the hydraulic dynamometer consisting of Trinanian bearings which going to support a shaft, and there is an inlet water medium, and there are radial blades, and there is a water level is there, and output is there not to release the water. And in the shaft there is a reaction arm which is going to uh, produce the force, and that force is measured using a device, force measuring device. Let us see. Basically the hydraulic dynamometer is one of the simplest form which acts as a water brake. The capacity of hydraulic dynamometer is a function of two factors. That means it governs two factors or two parameters, that is speed and water level. And torque is measured with the help of a reaction arm. As we see in the figure, the reaction arm is going to measure the torque that is produced. And the power absorption at a given speed may be controlled by adjusting a water level in a housing. And this type of dynamometer may be made considerably in larger capacities. That means whenever you are going to measure the high torque capacities of the water, or you are going to measure in a hydraulic fluids. So at that time, when the machine is going to operate with the help of hydraulic pressure, at that time in order to measure the torque, we are going to use the hydraulic dynamometer. Trinanian bearings, that means in order to support the shaft, there are bearings are used. That type of bearings are nothing but Trinanian bearings that support the hydro dynamometer housing, allowing it to rotate freely except for some restraint imposed by the reaction arm. The power absorbing element is in housing, which tends to rotate with the input shaft of the driving machine. That means that power absorbing element, that means reaction arm is there, so that is housed, which tends to rotate. That means input shaft of the driving machine is going to rotate continuously. So at that time it is going to tend to rotate after with respect to the input shaft, that has to be governed by the turning bearings. The rotation is constrained by a force measuring device, and such as simple forms of load cell scales are placed at the end of the section. That means whatever the force that is produced at the end of the shaft, that is measured with the help of a load cell or a scales placed at the end of the reaction arm. Coming to the advantages of a mechanical dynamometer. In a hydraulic dynamometer, constant supply of water running through the braking medium, which is acting as a coolant, and brake power of very large or a speed engine can be measured. In a hydraulic dynamometer there is a flexibility in controlling the operation. So hydraulic dynamometer is acting as one of the torque measuring device, force measuring device, so in which the water supply is continuously flowing, and which is acting as a coolant medium, and this is very flexible in controlling the operation, and it is going to measure the different forces produced in the running shaft. Coming to the pressure measurement. Pressure measurement, we know that in general pressure is nothing but force by area, that is represented by pascals or bar or Newton per meter square. Pressure is represented as a force by unit area exerted by a fluid on a container. Pressure are exerted by gases, vapors and liquids. So any medium, gas or vapors or liquids, any fluid medium, that is going to produce a pressure. Basically pressures are divided into different categories. One is absolute pressure, barometric pressure, total absolute pressure, negative gauge pressure of the vacuum, and positive gauge pressure, and there will be atmospheric pressure, and there will be a zero absolute pressure. So in the diagram you can see different pressures are categorized. Let us see one by one. What is atmospheric pressure? The atmospheric air that exerts a normal pressure on all surfaces within which it is in contact, that is nothing but atmospheric pressure. It is also known as a barometric pressure. And one more type of pressure is gauge pressure. It's a pressure measured with the help of a pressure measuring instrument, in which atmospheric pressure is taken as a datum line. That means atmospheric pressure, whatever the air exerts a normal pressure on surfaces, so that is taken as a datum here, and with reference to the atmospheric pressure we are going to measure the gauge pressure. The atmospheric pressure on the scale is marked as 0, and coming to the absolute pressure, Any pressure measured above the zero absolute pressure is known as absolute pressure. That means in the figure we can see the zero absolute pressure is a zero pressure line. So any pressure which is measured above the zero absolute pressure line is nothing but the absolute pressure. And in order to measure the pressures, so there are different devices are there. One is McLeod gauge. In a McLeod gauge, you can see there will be a mercury reservoir will be there. There will be a piston cylinder arrangement will be there. Due to the pressure difference, it is going to give the readings. McLeod gauge, you can see the vacuum space is there, and a capillary tube is there, and mercury is acting as a working medium, and there is a glass bulb is there. So in the capillary tube you are going to measure the pressure difference, that is what is the pressure is acting on a fluid, particular fluid we are going to measure is the McLeod gauge. Basically how it works, so using a Boyle's law, we know that P1 V1 equal to P2 V2. A known volume of a low pressure gas is compressed to a smaller volume, that means high pressure is created, and using the resulting volume and the pressure, the initial pressures can be calculated. This principle is the basic working principle for the McLeod gauge operation. The pressure to be measured, that means the total pressure which is acting on a fluid medium, that is nothing but the top reference column of the McLeod gauge. That means whatever the reference column is there in the McLeod gauge, in the figure you can see, so that is used to measure the pressure. The mercury level in the gauge is raised by operating a movable reservoir. That means that reservoir, movable reservoir is there, which can be made up and down, that is movable. So that is going to act as a rising medium for a capillary tube. When mercury level reaches the cutoff point, a known volume of gas, that means Vb, is trapped in the bulb, and the measuring capillary tube, that means whatever the total gas is trapped is, that is which is help in the rising the fluid level in the capillary tube. The mercury level is further raised by operating the movable reservoir, so the trapped gas in the bulb and measuring capillary tube are compressed. This is done until the mercury level reaches the zero reference point marked on the reference capillary. In this condition, the volume of gas in the measuring capillary tube is read and directly on the scales beside to it. In the figure you can see the movable reservoir is which is movable, that is lifted up or lifted down, so that creates a pressure difference, that makes the pressure, air pressure, that is trapped in the bulb to make the fluid to move up and down in the capillary tube. That's how you are going to get the fluid pressure to be measured in the scales, different scales. Some relations regarding the McLeod pressure gauge measurement. If the volume of capillary tube per unit length is A, then the volume of gas in the capillary tube is Vc equal to A into Y, where Y is the length of the capillary tube occupied by a gas. If the volume of capillary tube or a bulb or a tube down the openings is Vb, assuming isothermal compression, the pressure of the gas in the capillary tube is given by Pc. That is, pressure in the capillary tube is equal to the total pressure into Vb divided by Vc. The pressure indicated by capillary tube is again, we know that difference, that is nothing but whatever the measurement we have done, that is the height of the capillary tube Y, that is equal to Pc minus P, where pressure is expressing in terms of mercury column height. We know that P into Vb equal to Pc into Vc. By substituting the equation 1 and 3 in equation 4, we will get P equal to Ay square divided by Vb minus Ay. Usually we are assuming Ay is smaller than the Vb. Vacuum pressure P becomes Ay square divided by Vb. Thus the applied pressure is calculated using the McLeod gauge. This is the final expression by using which you can measure the total pressure, P equal to Ay square divided by Vb. Coming to the advantages of McLeod gauge, it is independent of gas composition. It serves as a reference standard to calibrate other low pressure gauges. and there is no need to apply the corrections to McLeod gauge readings. Coming to the limitations, the gas whose pressure is to be measured should obey the Boyle's law. Moisture traps must be provided to avoid any considerable vapor into gauge. It measures only a sampling basis and it cannot give a continuous output. These are the limitations for the McLeod gauges. These are the pictures which shows how the McLeod gauge is going to work, and these are the pictures. Let us coming to the Piranha gauge, that means thermal conductivity gauge. This is going to measure the pressure. You can see it is consisting of coils, that means compensating cell is there, some recorders are there, some electrical Keystone type of network is there. With the help of an electrical network we are going to measure the pressure. So there will be a platinum filament will be there, and upon which vacuum is applied and which has to be measured, and there will be a Piranha gauge chamber will be there, that means a measuring shell which is going to measure the pressure, and there will be a compensating cell which is going to compensate the power. There will be a power source. When the electric current is made to flow through a conducting wire, it gets heated. The rate at which the heat is dissipated from this wire depends upon the conductivity of wire and the surrounding pressure. At low pressure, the less amount of heat is dissipated, and high pressure heat dissipates. The main parts of the arrangements are a Piranha gauge chamber which encloses the platinum filament, a compensating cell to minimize variation caused due to the ambient temperature changes. The Piranha gauge chamber and the compensating cell is housed on a Wheatstone bridge circuit as shown in the diagram. So as I told, there will be a platinum filament, vacuum applied pressure will be there, and this is the unknown value, and compensating cell will be there, and there will be a measuring Piranha gauge chamber will be there, and using this one you are going to record the applied pressure. How it is going to work? A constant current is passed through a filament in the Piranha gauge chamber. Due to this current, the filament gets heated and assumes a resistance which is measured using the bridge, Wheatstone bridge. Now the pressure to be measured is connected to the Piranha gauge chamber. Due to the change in pressure, the conductivity and the temperature of filament will be going to change. When the temperature of the filament changes, the resistance of the filament also changes. Now the change in resistance of the filament is determined using the Wheatstone bridge, and this change in the resistance of Piranha gauge filament becomes a measure of applied pressure when it is calibrated. So using this principle, the pressure is measured. So Piranha gauge is also one of the thermal conductivity gauge which is going to measure the applied pressure or vacuum pressure. And coming to the strain, usually what is strain? We know that strain is the amount of deformation of the body due to an applied force. Change in the length or a change in the any mechanical property is nothing but a strain. Usually it is related to the length. Any elongation or deformation is related to the strain. That means the change in length to the original length is nothing but a strain. Usually we will represent strain epsilon in terms of epsilon equal to delta L by L. That means delta L is nothing but change in the length, and it is divided by original length, that is nothing but capital L. So total strain is epsilon equal to delta L by L. Strain can be positive, it is nothing but it can be tensile or it may be compressive. That means whenever you apply a force on a bar, the bar is going to elongate. That means its cross section is going to reduce. At that time the strain is elongated. That means it is a tensile strain. If you apply the forces in a compressive manner, so at that time the bar is going to contract. At that time its diameter is going to increase. At that time the strain will be compressive. That means strain can be, it may be tensile or it may be compressive. Although dimensions, strain is dimensionless. Strain is sometimes expressed in units such as mm by mm or inch by inch, That means finally the units are going to cancel, but it's expressed sometimes as mm by mm or inch by inch. In practice, the magnitude is measured. The magnitude of a strain measured is very small, and that's why its strain will be in micro strains. The strain often expressed in terms of a micro strain, that means 10 raised to minus 6, epsilon equal to 10 raised to minus 6. When bar is strained with a uniaxial force, as we see in the figure, a phenomenon is known as a Poisson strain, which causes the girth of the bar, that means uh, D, to contract in a transverse direction and perpendicular to its direction of the axis. The magnitude of this transverse contraction is a material property indicated by Poisson's ratio. Poisson's ratio is denoted by nu of a material, which is defined as a negative ratio of the strain in a transverse direction to the strain in the axial direction. That means nu equal to epsilon T divided by epsilon. Poisson's ratio for steel, for example, it is going to range. Its range is changing from 0.25 value to the 0.3. Usually, for steel and mild steel materials, the Poisson ratio is going to change from 0.25 to 0.3 value. Different types of strain gauges are there. Strain gauge is a device which is going to measure the amount of strain in the element or a mechanical device. It is going to work with the help of electrical resistance, and that is proportional to the amount of strain in the device. The change in length over a small gauge length is very small. A high magnification system is required. Based upon the strain gauges, they are classified as mechanical strain gauges, optical strain gauges, and electrical strain gauges. Coming to the mechanical strain gauges, it involves the mechanical means for a magnification. That means extensometer is used. Most commonly used mechanical strain gauges are a Berry type or a Hagen-Berger type. Let us see. These are one of the mechanical strain gauges. They are going to use the extensometer in order to measure the strains. There will be a dial indicator which is going to measure the total amount of strain, and there is a mechanical lever or a magnification lever which is going to acting as a magnifying the total material property. Whenever there is a specimen which is applied force in a tensile direction, that means whenever a tensile strain is there, there will be gauge points over which the two points are placed, and using the magnifying lever we are going to get the strain in the dial indicator. In the next session we are going to study about optical strain. Thank you and all. Have a good day.